morning, we were discussing about stability and control of an airplane. More explicitly, we were trying to understand the relationship between stability and control, whereby our own perception and our own understanding, using common sense, we understand that if a vehicle is statically stable, and if I go on increasing its stability, static stability, then to change its equilibrium from one known equilibrium to another equilibrium, I have to apply larger effort, because since it is highly stable, so it will always try to stay in that original equilibrium point. So if I want to make an aircraft highly maneuverable, so I will ensure that stability is not that high. In fact, all fighter airplane you will find it has negative static stability. So it is highly maneuverable. Okay? But we are talking about stable airplane here. And we are trying to understand the relationship between stability and control from designer's perspective. That is important. Okay? What we did was, so let's say this is that magic plate, George Calais plate, and let's say center of pressure is here and center of gravity is here. By now you are expert, you know, since center of pressure is ahead of center of gravity, so this is a case of statically unstable case, because very simple, you can check if there is a disturbance delta alpha, there will be a force here which will give a nose up moment, and the angle will further increase. It will not have any initial tendency to come back to the equilibrium. In contrast, if I put the center of pressure behind center of gravity, then you know this becomes a case of statically stable case. That is again you can check if this is the delta alpha disturbance you have given. Now there will be force here which will try to give nose down moment. So it has initial tendency to bring back the plate to normal equilibrium case where it was alpha equal to 0 or alpha equal to some fixed number. More important thing is any disturbance, it is trying to counter it, trying to make it 0. It has the initial tendency to make it 0, that whatever disturbance is there. So in a nutshell, you know, if I want to make an aircraft or this plate in particular, since we are talking about the plate here, to be stable, I must ensure the center of pressure is behind center of gravity. But the question is, suppose it so happens that center of pressure is ahead and center of gravity is behind. You have no options left to change the center of gravity. Assume that. It is true, because for an aircraft, we will be graduating from here to an aircraft, the center of gravity location is more controlled by the layout designer, because he has to have his options to keep chairs, then all those engines where he will put, where the cargo will be there, passenger seats, washroom, right, auxiliary units. So there is a generally, a layout engineer will not like too much of changing the CGs. Okay, so there is always fight goes on between a configuration designer and a layout designer, right? So let's say after that fight, they have decided this is the CG, now no more CG shift is allowed. So in such case, suppose center of pressure is ahead, then what do I do? Our understanding is very simple. If I want to make it statically stable, somehow I have to bring the center of pressure behind CG. Okay? So what I do, let's say I attach a rod and I add another small area at a distance, let's say LT, from the center of gravity of that plate. So now what happens? Whenever it sees some angle of attack, there will be some force acted here also, some force here. Now the resultant of these two forces will come back to this side, so our left hand side, and I can find out a point where I can represent the resultant as R1 plus R2. Let's say it's R1, this is R2, and I define that point as the center of pressure. That is, above that point, that moment is 0. So I can assume that whole resultant force is acting at that point, which is the center of pressure. Now, how much I should be able to draw this center of pressure backward for this total configuration will obviously depend upon the force here. That means the area of the fin here, or area of the tail here, and also on the moment arm, because after all it is the moment that will bring the center of pressure backward, because we are defining center of pressure at the point where total resultant will act. However, about that point no moment will act, like center of gravity. And we also realize that once I do like this, then I can write that overall center of pressure, let's say, has come backward. So it is statically stable. So our one problem that I want to make it statically stable is handled through another plate here, small area, but at a longer distance from the center of gravity of the whole this system. But next problem is severe, that I want to fly at different angle. I want to fly now at 2 degrees now. At some other instant I can have a requirement to fly at 5 degrees. So I have to change the angle. So again I have to change from one equilibrium to another equilibrium. But since we have designed it statically stable, so it will oppose, it will not allow by itself. That is the beauty of static stability. So to counter that, I have to generate additional force which will give a downward force and it will give a moment about Cg, and this moment should be good enough, equal to the whatever restoring moment coming because of static stability. And if I can make it balanced, then I can fly this whole system at some other angle. That is, I have now flying it like this, some alpha nu. This we have discussed, right? And we are very clear that somehow we have to apply this moment through this force to hold this airplane, because otherwise, since it is statically stable, if we don't have this force, it will try to come back to original alpha. And this is what, in a very holistic manner, the control problem. Okay? You can very well understand how much you can turn will also depend upon what is the force generating capability of this surface, or what is the moment generating capacity of this whole system through this. That will be decided by not only the force but also the moment arm. So these are a matter of details, right? If I have understood this, let us try to use it and try to see stability and control aspects of an airplane through this basic understanding. Okay? Again we go back to George Calais. So this is that magic plate, and let's say center of pressure is here and Cg is here. So I am taking a simple case that this plate is designed such a way that we have given more mass towards the nose of this plate, so that Cg is in front of center of pressure, or I say center of pressure is behind Cg, or center of pressure is aft of Cg. And this is, you know very well, this is statically stable case. Okay. Now let us try to represent this understanding through some formulation, so that a designer can use it very extensively. Okay. What we have seen, if there is a disturbance alpha, then it generates a force here. Actually, it generates a force through pressure distribution over this surface, but we are representing the overall effect by representing the total force acting at the center of pressure. Okay, that is the understanding. So what is happening? For positive angle of attack, if this plate has to be statically stable by itself, then it should generate a negative moment. Which moment? Negative pitching moment. What is the pitching moment I am talking about? If this is the airplane, like this is the x-axis and this is the y-axis, this is the pitching moment in the vertical plane. So positive alpha, and this plate will generate a negative moment. Negative moment means nose down moment, and positive moment by convention is nose up moment. So pitching moment, negative when I say, it is nose down. This is a matter of convention. Just take it like that. Similarly, if I have a negative alpha disturbance, that is, let's say something like this disturbance is coming, that is some gust is coming from the top like this. Okay, that will give a negative alpha. So now what will happen? Now because of negative alpha, air is coming like this, so it will generate some sort of a lift downward. And this will give what type of moment? This will give moment like this, nose up. So again you see it has initial tendency to ensure that this alpha goes to 0, the disturbance goes to 0. So again that means we have come down to a case where it is again a static stability case. And now for a negative alpha, what it tells you? That it should generate positive pitching moment. Right? Suppose I am going like this, positive alpha, negative pitching moment. So this disturbance is becoming 0. So initial tendency to make the disturbance 0. Negative alpha, if it is coming like this, then nose up moment. So this disturbance is becoming 0. So it is coming again back to alpha equal to 0 or whatever original alpha is there. So it has an initial tendency. So we said statically stable. So if I translate this in a graphical form, what should I write? I said the moment, if I write it moment here, I write it alpha here, I have seen for positive alpha, it is negative, for negative alpha, it is positive, and since this is symmetric plate, at alpha equal to 0, it is 0, so this will look like this. Okay? But you know, we don't work in terms of moment. We know that we are working in terms of non-dimensional coefficient, that is Cm. Like we don't work in terms of lift, we work in terms of Cl, lift coefficient. We work in terms of Cd, drag coefficient. So we will not work in terms of moment, we will work in terms of Cem, which is pitching moment coefficient. How do I define Cm? As simple, the pitching moment, which is m here, divided by half rho v square s into chord. We call it mean aerodynamic chord. It is important, you will understand, all wings are not rectangular, so there will be a tapering of wing. So it's something like an average chord. At this stage you understand that much. Okay. So now what I will do when I plot this m versus alpha, instead of m, now I will use Cm. It's a matter of dividing that pitching moment by this number. And to give little more of insight on C bar, which I think I will give you more on during the little bit of addition to design aspects, right? But at this stage, to give you some feel, say this is the rectangular wing, this is the span you know by now, and this is the chord, okay? Now you will find there are wings like this. So here, if I call this root chord CR, I call this tip chord CT, they are not same. For a rectangular wing, they are same. So it was very easy for me to talk about C. But here, because this chord is changing at each station, so we define something called mean aerodynamic chord, and that is exactly we are writing here with a bar, right? And it's the mean aerodynamic chord of the wing. So I can write CW also. And now with this diagram you can understand in an average sense, this is a weighted average chord of the wing, and mathematically it is defined as, don't give too much of weightage to all this integral now, try to understand what is the meaning of this and why is the span, okay, direction. So it is weighted by the chord. For you and me at this stage, assume that this is an average chord which will help me to visualize as if it's a rectangular wing with C bar and B as a configuration parameter. Okay, let's stop this discussion here only. And you also understand why we have divided by C. That is because this is the moment I want to convert to Cm. So I have to divide this by half rho v square into S. This is the force. So I have to have one length, and that is why divided by C bar, so that it becomes non-dimensional. Now come back to this. This is important. Focus your attention here. Let me draw this little bigger, because this is most important part of today's lecture. Whatever I have said just now, till now, already I have discussed in the last lecture. So now let us very carefully understand this concept. What we are saying, this is the CG, and CP is here, and it is like this. We know it is statically stable. I am now translating this to behavior of pitching moment coefficient with angle of attack. And what we have noticed, that for alpha positive, Cm is negative. For alpha equal to 0, Cm equal to 0. For alpha negative, Cm is positive. So if I try to plot this, then alpha positive, Cm negative. Let's say let me take somewhere here. So I will get a graph something like this. Okay? Alpha positive, Cm negative, alpha negative, Cm positive, alpha equal to 0, Cm is 0. Satisfying these three conditions. Very simple. Now I will try to see whether this representation indeed tells me that the aircraft or this plate has static stability. Now recall, how do we define static stability? We said if a system is disturbed from its equilibrium point and if it has initial tendency to come back to the equilibrium, then this system is statically stable. Very simple. So what is the catchword? Catchword is equilibrium point. How do I find which is the equilibrium point here? Do you think this is equilibrium point? If I see this point, there is a unbalanced moment here. So this cannot be equilibrium point. Can this be equilibrium point? No, because at this point there is a unbalanced moment. So what is the equilibrium point? Equilibrium point here is that point where Cm is 0. So this is the equilibrium point. Okay? This is the equilibrium point, or we also call it trim point. Now let us see what is the definition. If I disturb the system about its equilibrium and if it has initial tendency to come back to the equilibrium, I'll say it is having static stability. The catchword is if it has initial tendency to come back to equilibrium. Let's say I have given a disturbance here. It was 0, alpha equal to 0, some alpha 5 degree or something I have given a disturbance. So what will happen immediately? Immediately this aircraft will generate, or this plate will generate negative moment. Correct? Negative moment will do what? It will try to, plane was going like this, there is a positive alpha disturbance, so it is generating a negative moment, so the nose will come down. So you could see it has initial tendency to make this situation where it again becomes alpha equal to alpha original, so it is nullifying. It has initial tendency to nullify this disturbance. Okay? So you say yes, that means if it generates negative moment, the alpha will go on reducing, so it has a tendency or initial tendency to come back to this equilibrium point. Similarly, if it has a negative disturbance, let's say here, it will generate a positive moment, nose up. Again it will try to go towards this point. So indeed, about this equilibrium, this aircraft or this plate is having static stability. Is it clear? Okay. Now there is a little finer thing you must understand. Whenever I am talking about moment, okay, what is moment? Moment is an effect of a force about a point or a line. Okay. So this moment, when I am writing Cm, it must be about a point for the airplane, and this is actually is about center of gravity. If you take this plate for this example, whatever Cm I am writing here, it is about the center of gravity. Why I am taking center of gravity? Because I know in free air, free space, the body will rotate about an axis passing through center of gravity. So this is the variation of Cm about Cg with angle of attack alpha. So when I draw Cm versus alpha, I must mention that this is for a given Cg location. So I am writing xCg1. Now think of a situation. Suppose I start drawing the center of gravity backward. What will happen? As I try to draw center of gravity backward, so distance between Cp and Cg is going to reduce. So its initial tendency through the moment will increase or decrease for the same alpha. Because this moment arm is reducing. So the initial tendency will reduce. So what will happen? As I am moving Cg backward, this slope will try to flatten out. And there will be a point when this CP and CG come to a same point, that is they are considered. So I am moving this here. When the CG and CP coincides, then what is the restoring moment? There is no moment arm, so it is 0. So that time it becomes neutrally stable. So there won't be any moment. Whatever disturbance you give, the slope of this line will become 0, or it will become parallel to the x-axis. So what is the message here? Message here is, whenever I am talking about Cm versus alpha, I should be very clear about what point. It is basically about center of gravity. And as I move the center of gravity closer to center of pressure, it will have an effect in terms of reduction in static stability. And there is a point which is for this plate the center of pressure. If I bring the CG to center of pressure, this plate will become neutrally stable. Okay? So I can define neutral point by using this understanding. Neutral point means the CG location at which the plate or the aircraft will become neutrally stable. So with this background, now let us try to add little more understanding on this graph. So what we have learned by this, whenever we are drawing Cm, it is actually CmCg, and alpha, whenever I am drawing a graph like this, I should know that it is about a particular CG. And for this plate or the aircraft to be statically stable, what is the condition? Condition is the slope of Cm versus alpha graph should be less than 0 at equilibrium. This is very important. So what do? I check what is the equilibrium. Equilibrium is at Cm equal to 0. Now I check the slope of Cm versus alpha at equilibrium. I find yes, it is indeed negative. So I say this is a case of static stability, or this configuration is statically stable. Remember, there could be cases, again CmCg alpha, there could be cases something like this. Typically, if you see parafoils and all, the Cm versus alpha could be like this. Now if I ask you whether this system is statically stable or not, how will you answer? Again you have to find out what are the equilibrium point. So now you see equilibrium point means the point where Cm is 0. So one point is here, Cm is 0, another point is here, Cm is 0. Please understand, we are talking about static stability. Purposefully we have taken cruise as our equilibrium. This you should remember. So now if I try to see here whether this configuration is statically stable about trim 1 or not, we have to check what is the slope of Cm versus alpha at this point. If it is negative, it is statically stable. Now you check here, yes indeed slope is negative, so it is statically stable here. But if I come to the second trim point here I see that at the trim, the Cm versus alpha or slope of this line is positive. So about this equilibrium, this configuration is not statically stable because it will not have an initial tendency to come back. You can check here, if I give a disturbance, suppose the angle of attack increases, then this will generate positive pitching moment. The positive pitching moment will further take the angle. So no initial restoring tendency. That is why if the slope is positive at trim, we say this is statically unstable. This example is typically true for parafoils and highly nonlinear type of configurations. Just to give you the importance of checking stability about trim point, I have given this example. Okay, for aircraft, for most of the aircraft, will be having train like this. So from this point, now you forget about this graph at all.